Okay, let's dive right into this fascinating explainer. Today, we're unpacking a breakthrough paper that literally transforms how machines solve some of our most complex, highly conflicting mathematical problems. Optimization is practically everywhere in our modern world, right? And today, we're looking at this incredible method where computer scientists actually turn to nature, specifically swarms of grasshoppers, to teach algorithms how to search for the ultimate mathematical compromises. It's this wild journey from dense algorithms to the beautiful simplicity of the natural world, and I am so excited to guide you through it. So think about everyday engineering for just a second. We all want a car that's the absolute fastest in the world, but we also want it to be the most fuel efficient. Or, maybe a power grid that is simultaneously the cheapest to operate and the most reliable. These are what we call multi-objective optimization problems. And the catch is, their goals inherently conflict. You really can't maximize one without hurting the other. So how exactly do engineers program a computer to find that perfect compromise? I mean, when there isn't just one single right answer, how does a machine know when it's finally found the best possible set of solutions? To get there, we're going to follow this quick roadmap. First, the optimization dilemma. Second, getting inspired by grasshopper swarms. Third, the divide, share, and conquer approach. Fourth, benchmarking the algorithm. And finally, the real-world engineering impact. All right, jumping right into section 1, the optimization dilemma, balancing conflicting goals. Before we can really understand how the algorithm works, we need to know what it's actually trying to achieve. Because we can't just have one single perfect solution. The algorithm's ultimate goal is to find what mathematicians call the Pareto optimal front. Picture a curve on a graph representing the absolute limits of what's possible. Every point on that boundary is a non-inferior solution. Basically, if you want more speed, you absolutely have to give up some fuel efficiency. The algorithm needs to hand human engineers a really diverse, perfectly spread out set of these top-tier compromises so we can make the final call. Honestly, finding this front quickly and accurately, that is the absolute holy grail of this field. Which brings us to section 2, inspired by grasshopper swarms, nature's search algorithm. So, to search for that elusive Pareto front, computer scientists developed the grasshopper optimization algorithm, or GOA. It's a meta-heuristic method. That just means it uses rules inspired by the swarming behavior of actual grasshoppers. You know, how they interact, how they're pulled by gravity, riding the wind, to digitally navigate through this massive sea of mathematical possibilities. But to make this actually work, these simulated bugs face a constant tug-of-war between two different modes, exploration and exploitation. Exploration is your wide search, wandering broadly to discover totally new areas that might hold the ultimate prize. Exploitation, on the other hand, is a deep search. That's staying put and intensely focusing on a high-quality area you've already found to squeeze out the absolute best result. Even digital bugs have to figure out whether to keep wandering or stop and eat. And, well, here lies the big problem with the original algorithm. The standard GOA uses a single parameter, often called parameter C, to manage this delicate balance for the entire swarm all at once. Usually, it just kind of linearly transitions the whole swarm from exploring early on to exploiting later. Basically, the base algorithm forces the entire swarm to behave the exact same way at the exact same time. And actually, that's a massive bottleneck. When you're facing highly complex, multi-objective problems with tons of misleading local optimums, this rigid, single-minded approach causes the digital swarm to get completely trapped, or it forces it to converge way, way too slowly. Let's move right along to section 3, divide, share, and conquer, the MOGOM-MC upgrade. To fix this bottleneck, the researchers came up with a genuinely brilliant upgrade using what they call a multi-group and coevolution framework. This three-step process is really the core breakthrough here. Instead of treating the swarm like one giant monolithic entity, they divide the population into multiple subgroups. Then, they assign entirely different mathematical behaviors to each group. Like one group might use a linear parameter, another a cosine adaptation, maybe a third uses an arc adaptation, and finally, after searching in parallel, the subgroups actually communicate. They share their absolute best and worst solutions, allowing the whole system to co-evolve. By setting it up this way, the swarm is simultaneously exploring widely and exploiting deeply. It's super clever. As the source material points out, this adaptability is absolutely the magic ingredient. Think about it. In the real world, engineers almost never know exactly how a complex problem is going to behave before they try to optimize it. This framework gives the swarm the power to tackle unknown, highly complex problems totally organically. The algorithm just figures out the right balance on the fly without needing constant, tedious manual tweaking by the engineers. Okay, jumping into section 4, benchmarking the algorithm. essentially proving the upgrade. Because, look, academic theory is one thing, right? But did the multi-group upgrade actually work in practice? Well, to find out, the researchers put their new algorithm through a rigorous set of tests. They pitted their new multi-group Grasshopper algorithm against the standard single-parameter versions using these incredibly complex, standardized multi-objective benchmark functions. These are basically famous mathematical obstacle courses designed specifically to trick and trap optimization algorithms. To keep score, we're going to focus specifically on the IGD metric, or inverse generation distance. This calculates the literal Euclidean distance between the solutions the algorithm actually found and that true mathematically perfect Pareto optimal front we talked about earlier. It tests both convergence, so how close it got to the true front, and diversity, meaning how well the solutions are spread out. And remember, for IGD, a lower score is better. A low score means the digital grasshopper successfully found more accurate and much more diverse solutions. And when we look at the data from the famous ZDT1 benchmark function, the results are honestly pretty stunning. The multi-group framework, labeled MOGOAR here, absolutely crushed the baseline. The standard version scored a 0.0081, while the upgraded multi-group version achieved a drastically lower 0.0016. It wasn't just a fluke either. Across nearly all the benchmark tests, whether they were unimodal, multimodal, or these crazy complex composite functions, the multi-group and co-evolution approach significantly outperformed the rigid, older models. Now you might be thinking, hey, if dividing the swarm is good, why not divide them into 1,000 tiny groups? Well, through extensive sensitivity analysis, the researchers found that dividing the swarm into exactly 3 to 5 subgroups is the absolute sweet spot. It's the Goldilocks zone. If you divide them up too much, the simulated grasshoppers actually start repelling each other way too frequently. The computational time shoots up without actually improving the accuracy of the final solutions. Nature thrives on balance, and as it turns out, so does this algorithm. Finally, let's wrap things up with Section 5, Real-World Engineering Impact, moving beyond the math. So why does all this dense mathematics, Pareto fronts, and digital grasshoppers actually matter to you and me? It matters because algorithms exactly like this are the invisible engines running our modern society. By perfecting this multi-group framework, engineers can now automate and optimize massive, conflicting systems with so much more efficiency. This directly translates to very tangible tech applications. We're talking about helping select the right features when training smarter machine learning models and neural networks. It optimizes wild, complex manufacturing schedules, balances the load and stability of our actual power grids, and dictates advanced engineering designs where cost and performance are just locked in this constant battle. It's truly an incredible reminder of how deeply connected everything is. The blueprint for designing our absolute most advanced, complex digital technology might just be waiting right outside in our own backyards, perfected by millions of years of evolution. The researchers solved a cutting-edge computer science bottleneck simply by allowing their digital swarm to behave a little more dynamically, a little more naturally. So it really leaves us with this final thought. If simulating the swarming habits of grasshoppers can optimize our power grids in AI networks, what other secrets is nature waiting to teach our machines? Thanks so much for joining me on this explainer, and definitely keep questioning the world around you.